So I'm going to slowly sort of like get started. Thanks everyone for coming to LATA, of course, the third iteration of this workshop. And I think we have a pretty great schedule lined up for today. So we have 6 talks in total. We'll have a poster session starting at 10:35-ish. Whenever the 2 talks end, we'll just do these quick elevator pitches. This is something new we're trying where the people who have posters will just say a few blurbs about their poster before we go out into the lobby for the poster session. And then we have a lunch and a coffee break after that, and 4 talks after the poster session. In terms of the accepted posters, we have 8 that we're looking forward to learning more about. So I'll come back to this, but I think for the time being, I'm gonna pretty much hand it right over to our first speaker. So for our first speaker, we have Eric Balkanski. Eric is an assistant professor in the Department of Industrial Engineering and Operations Research at Columbia, affiliated with the Data Science Institute. He received his PhD in computer science from Harvard University, where he was advised by Yaron Singer. His research interests include combinatorial optimization, algorithm design, mechanism design, and machine learning. And today he will talk about mechanism design with predictions. So let's welcome him.
Thanks. Thank you for the introductions. So today I'm going to talk about how the framework of algorithms predictions can be used in the context of mechanism design problems. And please interrupt me at any time with questions during my talk. And this talk will be based on the following 2 papers. The first one is with Priyanka Goral, Vasilis Katselis, Tingtingu and TJ Tan, and the second one was Vasilis Katselis and Gurnu Shakarami. Okay, so since this is the first talk of the workshop, I figured I would give a little bit of background on algorithms predictions. In algorithm design, the standard performance measures that we use to mathematically evaluate algorithms are mostly based on worst-case analysis. On the positive side, worst-case analysis, they give very strong robustness guarantees that can hold for any instance. However, on the other hand, they can also often be very pessimistic due to pathological instances that we don't really see in practice. On the other hand, we have machine learning. Machine learning works typically very well in practice, but it often suffers from not having any worst-case guarantees, which in applications where we really care about robustness can be problematic. So the framework of algorithm prediction, the main goal is to try to combine the benefits of algorithm design and machine learning and to try to aim to get the best of both worlds of both of these fields. So in this framework, an algorithm, in addition to be giving the standard input, is also going to be given some machine learning predictions about the instance at hand, okay? And this prediction can potentially be erroneous. And now the goal is going to be to achieve some improved performance guarantees when these predictions are accurate, while also having robustness guarantees that hold even if these predictions are completely wrong. Okay? So these 2 goals are formalized by the performance measures of consistency and robustness, which are the 2 main performance measures that are used in the field of algorithms predictions, and that were formalized by Todoros and Sergey, who are participants in the workshop today. So consistency is the worst-case performance of an algorithm's prediction when the predictions are exactly correct. And robustness is going to be the worst-case performance overall when the predictions can be completely wrong. Okay? So these are 2 extremes, and more generally, we also want to try to get guarantees that smoothly interpolate between consistency and robustness as a function of the prediction error. So one area where algorithms prediction has been particularly successful is in online algorithms. So in online algorithms, we face some information limitation that are due to uncertainty about the future. And predictions here can be used to try to overcome these information limitations. So in online algorithm with predictions, at each time step, we may have to make some irrevocable decision as online algorithms. But now we're given some predictions about the future that are potentially erroneous that we can use to make some decision. So in this talk, my goal is going to be to show you that another area that can really benefit from the framework of algorithm-based prediction is mechanism design. So in mechanism design, we also face some information limitations, but now they are due to the participating agents that have private information that are not known to the designer. Okay? So what I'm going to call mechanisms is just algorithms where the input is provided by strategic agents. Since we would like the strategic agents to report truthfully, we often aim to design mechanisms that are strategy proof. So what is strategy proofness? It simply says that for each agent, no matter what the other agents report, an agent cannot benefit from misreporting their input. Okay. So now when we augment mechanism predictions, now an input to the mechanism is going to be the agent's private information, the agents who report their private information as a mechanism design. And now in addition, we're going to be given some ML prediction about the instance at hand. And our goal is still going to be to try to design mechanisms that are strategy proof. So over the past 3 years, this area of mechanism design with predictions has been growing very fast for multiple different, and there's been multiple different mechanism problems that have been studied with predictions, including strategic facility location, auctions, scheduling, social choice, assignment and allocation, and strategic learning. There's this great resource. This website is a great resource to find that keeps track of all of the papers in the area of algorithm predictions. And if you want to see all of the papers in this area, you can filter for game theory and mechanism design, and you will find all of these papers. So for today, I want to focus on one specific mechanism design problem. This is going to be for the problem of strategic facility location. Okay. And so first, I want to just introduce the problem of strategic facility location. And I will do that even start by defining the problem in the non-strategic setting. So we're going to have n agents. And each agent is going to have a preferred location for where they would like a facility to be placed. So throughout this talk, there is n preferred locations of the agents. They're going to be these black dots. The goal of the mechanism is going to choose a location to place a facility. So here, this yellow star. And the cost that each agent is going to incur from where a facility has been placed is going to be its Euclidean distance between its preferred location and the location of the facility. Okay. In facility location, there's been two objectives that have been mostly studied. The first one is the egalitarian social cost, where the goal is to minimize the maximum cost over all of the agents. So we want to minimize the maximum distance to the location. And the other one is the utilitarian social cost, where we want to minimize the average cost over all of the agents. So this is the facility location problem that we're going to look at. Now, in the strategic version of this problem, the preferred locations of the agents are private to each agent, and they have to be reported to the mechanism, and they can potentially and the agent can potentially misreport these preferred locations. Any questions about the problem of strategic facility location? Great. So here's going to be the outline for the rest of the talk. We're going to look at both the egalitarian social cost and the utilitarian social cost objective augmented with predictions. And our goal is going to be to achieve optimal consistency robustness trade-offs. And what we're going to see is that the settings in which we can get optimal consistency robustness trade-off is going to depend on whether we focus on deterministic or randomized mechanism and what kind of metric space we're considering. Okay, so there's going to be some settings where we're going to be able to exactly characterize the consistency robustness Pareto frontiers, and some others where we're going to have some interesting open problems that I will mention. So let me start with a warm-up. We're going to consider deterministic mechanism for the line metric. So here, all of the points are going to be on a line, and we're going to have to place the facility on a line. So this is the 1D case of the problem. And as we're going to see, this is going to give us a pretty nice, simple setting as a warm-up. So first, what is happening without predictions? So here, again, we're going to start by focusing on egalitarian social cost. So we want to minimize the maximum cost of all of the agents. In the full information setting where we don't have strategic agents, it's pretty easy to see that the optimal location should just be at the midpoint between the leftmost and rightmost point if you want to minimize the maximum distance to any of the points. Now, if you choose this midpoint between the leftmost and rightmost point, this is not going to be strategy proof. How can you see that? If you were the leftmost point, what you could do is just misreport your preferred location to the left. This would drag the facility towards you, and you would benefit from misreporting. Okay, so this is not strategy proof. Now, another mechanism that is strategy proof is the median mechanism. So the median mechanism simply just placed the facility on the median point over all of the points. So it finds a median and then just place the facility on this median preferred point. Now, it's not too hard to see that this mechanism is strategy proof. And it achieves a 2 approximation, okay? So the maximum cost incurred by this mechanism is going to be at most twice the maximum cost incurred by the midpoint solution. And now this 2 approximation is actually optimal among deterministic strategy proof mechanisms. So if you check yourself a deterministic mechanism, you cannot do better than this 2 approximation, okay? And so now what we're going to ask is, can we use predictions to improve this 2 approximation? So the first question should be what's going to be our predictions? One natural notion for our predictions could be to have one prediction for each of the agent's preferred locations. In this talk, we're going to focus on a weaker prediction notion where we're going to be just giving a prediction about the location of the optimal facility. And this is a weaker notion. You can easily see that if you're given prediction about each of the agent's preferred location, it would be easy to compute predicted optimal facility location. So unless otherwise specified, we're going to focus on this prediction. So now consistency is going to be the approximation ratio that is achieved by the mechanism when the prediction is exactly correct, and robustness, the approximation ratio achieved by the mechanism when the prediction can be arbitrarily wrong. So what are some trivial guarantees that we can achieve here? One approach is that you can completely trust the prediction and just return the predicted optimal facility as your facility. Now, this would perform very well when the prediction is correct. It would be optimal when the prediction is correct. But if the prediction is arbitrarily wrong, this can be arbitrarily bad and you get unbounded robustness. On the other hand, you can just completely ignore the prediction, just run the median mechanism and get to consistency and to robustness. So this leads us to our 2 main questions. Can we get a consistency that's better than 2 and by robustness? And more generally, what is the trade-off between robustness and consistency? Okay. Any questions about our setup? Good. Okay. So here's the first attempt. And here's something that you can do actually in mechanical errors prediction that you cannot do in online algorithms prediction. One thing you can do here is that actually when you're given a prediction, you can check if your prediction is correct. You're given the reports of all of the agents, and now you can see based on this report, is the prediction correct or not? So you can immediately check if based on the reports it's correct or not. Since you can check if the prediction is correct or not, maybe like tempting approach would be to say, well, I check if the prediction is correct or not. If it's correct, then I'm just going to use it. And if it's not correct, then I'm just going to ignore it, okay? So if it's correct, then I'm just going to return the predicted optimal facility location. Otherwise, I'm just going to run a median mechanism. Now, what is the issue with this approach? It's not going to be strategy proof, right? One participating agent might, if the prediction is accurate, might try to misreport to pretend like the predictions are wrong if they would benefit from having the output of the median mechanism rather than the predicted optimal facility location. Okay, but this is not going to work. So here's going to be our deterministic mechanism with predictions for the line. It's going to be pretty simple. What we're going to do is that we're going to have 2 cases. In the first one, if the prediction is between the leftmost and the rightmost point, we're just going to return the prediction. If the prediction is outside of the interval between the leftmost and rightmost point, we're just going to return the point that is the closest to the prediction. Okay? So we're just going to find a point in the interval between the leftmost and rightmost point that is the closest to the prediction and return that point. Okay? This is going to be our mechanism. What are the guarantees achieved by this mechanism? This mechanism, we can show that it is strategy proof, one consistent, and two robust. Okay? So this is actually the best of both worlds. When the prediction is accurate, we get the optimal solution, and it can be arbitrarily wrong, and we recover the optimal two robustness that we know that we cannot do better due to the two lower bound for deterministic mechanism. Okay. Now, the proof of this result is very simple, so I'll just quickly go over it. For the one consistency, it's easy to see that if the prediction is correct, then it has to be between the leftmost and rightmost point. So we're going to return the optimal location. For the two robustness, we're always going to be guaranteed by this mechanism that it's going to return a point that's between the leftmost and rightmost point. If you return a point between the leftmost and rightmost point, then your maximum cost is going to be at most the length of this interval between the leftmost and rightmost point. The cost of the midpoint solution, which is the optimal solution, is going to be half the length of that interval, so you get a two approximation. Now, why is it strategy proof? Without loss of generality, consider a preferred location of an agent that's on the right of where the facility is placed. Now, there's two different things that this agent could try to do if they're going to misreport, either misreport to the right or to the left. If they misreport to the right, then this won't change the location of the facility, so they won't benefit from misreporting. If they misreport to the left, the only thing how this can affect the location of where the facility is placed is that they can just push the facility more towards the left, which would just hurt them, so they wouldn't benefit either. So in other words, any agent cannot benefit from misreporting, and this mechanism is strategy proof. Okay. So more generally, we can also get a result that interpolates between consistency and robustness as a function of the prediction error. So our notion of prediction error is going to be the distance between the true location of the optimal facility and the predicted optimal facility normalized by the optimal cost. And we're going to get an approximation that is the min of 1 plus the prediction error and 2. So when the error is 0 and the prediction is perfect, we recover our one consistency. And then as the error is small, we get something that still improves over the two robustness. And as the error is very large, we recover the two robustness. Okay, so this was our warm-up for the case of deterministic mechanism on the line metric. Hopefully it gives you some simple intuition of what's going on for this problem of facility location predictions. Now, the next thing I'm going to want to consider is the randomized mechanisms for the line. What if now you allow for randomization? So first, it turns out that if you allow for randomization without prediction, you can improve over the two approximation. Sorry. So there's this cute mechanism called the LRM mechanism. What it does is that it's going to return the leftmost point with priority 1/4, the rightmost point with priority 1/4, and the midpoint between L and R, which is the optimal solution, with priority 1/2. Now, it turns out that these priorities were carefully selected to exactly balance out the different costs so that this mechanism is truthful in expectation and actually achieve the 3.5 approximation. So with this randomization, you can maintain truthful expectation and improve the approximation from 2 to 3.5. And again, this 3.5, it turns out to be the best approximation achievable by any randomized mechanism that is strategy proof. Okay, so what have we seen so far? With that prediction, we can get, with the randomized mechanism, we can get a 3.5 approximation. And before we saw a 1 consistent and 2 robust deterministic mechanism. Now, a first trivial mechanism that can give you some kind of guarantees is to run with some probability P this LRM mechanism. And then with the remaining probability, just run the 1 consistent and 2 robust mechanism. right? And our main result for randomized mechanism is that this is actually the best you can do, okay? We can show that no mechanism for the line that is one expectation and that guarantees on 1 plus delta consistency, then no such mechanism can also guarantee a robustness that is better than 2 minus delta. And this is true even if you're provided with prediction about each of the agent's preferred locations. So this trade-off actually matches the guarantee of the simple mechanism that I just mentioned in the previous slide. And so this gives us a complete characterization of the consistency robustness Pareto frontier. It also tells us that the full predictions do not help compared to the predicted optimal location, okay? So since the mechanism here that we have only uses a prediction for the optimal robustity location, and this result holds even if you give in a prediction about all of the agent's location, we get matching bounds. This tells us that the full predictions do not help. So having more information about the predictions doesn't help. Okay, so this kind of like gives us a complete understanding of the optimal trade-off between consistency and robustness, both for deterministic and randomized mechanism for the 1D case. So let's move on to higher dimension. And let's start by looking at deterministic mechanisms in the higher dimension. So first, without predictions, there is a generalization of the median mechanism that is called the coordinate-wise median mechanism. So how the coordinate-wise median mechanism works is that along each coordinate, it's going to look at the median of the points on that coordinate independently. So what it's doing is that along each dimension, it's going to run the median mechanism along that dimension and then aggregate all of the medians along each dimension to get a solution. Now, this coordinate-wise median mechanism achieves a two approximation. The two approximations from one dimension extends to any dimension. So we still get a two approximation without predictions. Now, we're also able to generalize a mechanism that achieves a one consistency to robustness to higher dimensions by doing the following. Now, what we're going to do is that we're going to build a minimum access parallel bounding box that contains all of the points. If the prediction is inside of that box, then we're going to return the prediction. Otherwise, we're going to return the point in that box that is closest to the prediction. Okay, so it's like we're projecting if the prediction is outside of that box, we're projecting the prediction onto that box. So now what are the guarantees that we achieve with this mechanism? In any dimension, this mechanism is going to be strategy proof, one consistent, and achieve a 1 plus square root of D robustness. So here, the main thing I want to emphasize is that unlike the 1D case where we were able to get optimal consistency without any loss in the robustness, here to get one consistency, we do have some loss in robustness since the optimal robustness that we can achieve is 2 without predictions. Here we're going from 2 to 1 plus square root of D, okay? So now the next question is like, is this loss necessary if we want to get one consistency? And the answer is actually yes. And it's not just to get one consistency. For any mechanism, if you want to achieve better than 2 consistencies, so if you want to use predictions to outperform the coordinate-wise median mechanism that doesn't use predictions, then you cannot do better than 1 plus square root of D robustness, okay? Now, one thing I want to emphasize is that this holds, you need some assumption on the family of mechanisms you consider. This holds for deterministic, anonymous, and strategy-proof mechanisms. So what are anonymous mechanisms? They're simply saying that this is for mechanism where the identity of the agents doesn't matter. More formally, it's just saying that the mechanism is an invariant over permutations of the agents, okay? And all of the mechanisms that I've mentioned so far, they are all anonymous. So the proof of this result is, again, relatively simple. So let me quickly go over it. For the one consistency and strategy proofness, it's going to be the same argument as for the line. Now, for the 1 plus square root of D robustness, what we're going to be looking at, I want you to think about the smallest sphere that contains all of the points. Now, if you look at the smallest sphere that contains all of the points, then the center of that sphere is going to be the optimal facility. Okay? Now, if you want to look at the maximum distance between any point and the location that is given by the mechanism, you can upper bound it by the triangle inequality, by the distance between that point and the optimal facility, and plus the distance between the optimal facility and the point that's given by the mechanism. The distance between a point and the optimal facility is, by definition, at most opt. And now the distance between the optimal facility and the point given by the mechanism is going to be at most square root of d times opt, because we know that this point has to be inside of the bounding box that contains all of the points. And so now if you add these two, you get the 1 plus square root of d bound for the robustness. Okay? So this was for the positive result. For the harness result, I won't have time to go over the proof in detail, but what it does is it's going to use the following very useful and elegant characterization of all strategyproof mechanisms for facility location. So there's this nice result from 93 that says that a mechanism is deterministic, anonymous, unanimous, and strategyproof if and only if it is what's called a generalized coordinate-wise median mechanism with n-1 constant points. Okay? Now, I don't want to go into the details of what exactly is this family of generalized coordinate-wise median mechanisms, but I just want to point out that it is very useful characterization of strategyproof mechanisms for facility location that we can use to achieve impossibility results. Okay, so now, again, here we were able to get an optimal trade-off between consistency and robustness. How about randomized mechanisms beyond the line? So when we start thinking about randomized mechanisms beyond the line, we first encountered the following, I think, interesting observation that is pretty, I think, counterintuitive. You would, of course, think that our lower bound, the lower bound that we have of 3/2 for 1 dimension would, of course, also hold in two dimension, right? Anything in 1 should hold in 2D. Well, we were actually not able to extend the lower bound in 1D to hold also in 2D, which we thought it was pretty surprising. The main reason for that is because the design space of 2D mechanisms is much richer than the design space for mechanism in 1 dimension. So now, of course, what you would think about doing, right, is that if you have a hard 1D instance, you just embed it into 2 dimension. Now, the optimal facility would still be on that embedded line that is in 2D. But now the issue to extend our lower bound is that you can potentially use a location that is not on this line, and that could allow the designer to affect the incentives of the agents in new and non-trivial ways. So for example, hypothetically, you could maybe imagine that a mechanism would try to punish somebody who tries to misreport by putting the facility way outside of the line to make them incur a larger cost. Okay. So this is kind of like an informal argument for why we were not able to extend the 3/2 lower bound in 1D to higher dimension. We were able to get for 2 dimension a lower bound of 1.118 for any truthful and expectation mechanism. And so here the main thing to note is that there was no previously known lower bound for 2 dimension, and this best existing lower bound for 2 dimension of 1.118 is weaker than the best known impossibility result for 1 dimension of 1.5. Now, what about mechanism? What about upper bound? So you can actually slightly outperform the 2 approximation that's achieved by the coordinate-wise mechanism if you allow randomization. You can actually achieve 2 minus 1 over an approximation with the following mechanism that's called a centroid mechanism. With priority 1/2, you're going to return the point that's the average of all of the points, which is called a centroid. And otherwise, what you're going to do is that you're just going to run the randomized dictatorship mechanism. So how this mechanism works is that you're going to pick one agent at random, as you're just going to allow them to pick their preferred point. and this actually the 2 minus 1 over n, you slightly outperform the Cornelian-wise mechanism. And so it is an open problem to close this pretty large gap between the best known lower and upper bound for a 2D randomized mechanism of facility location without predictions between 1.118 and 2 minus 1 over n. Okay, so now if we allow some prediction, here's going to be our mechanism. So we call it the centroid mechanism on extreme agents. But how this mechanism is going to work is going to be an extension of the centroid mechanism. We're going to return with probability 1/2 the centroid, but now we're going to do randomized dictatorship on a subset of the agents that is carefully selected. So what is going to be the subset of agents who we're going to consider? We're going to look at the K agents who suffer the maximum cost with the predicted optimal solution. In other words, if you look at the predicted optimal solution, and then you build the smallest sphere that is centered at this predicted point that contains all of the points, then you would look at all of the agents that are on the border of that sphere. And this mechanism, what it achieves, it is 1.67 consistent and 2 robust. And if there's only 2 points on the border of that sphere, which you would expect to have in with high probability if you have any kind of like random instance, then the consistency improves to 1.5. So here's a recap for all of our results for the egalitarian cost. The main thing here I want to emphasize is that for all of these results, except for randomized 2D, these we get the optimal consistency robustness trade-off, and it's still open whether we can improve these 2 bounds, which I think should be possible to improve. Okay, so now let me briefly mention the utilitarian social cost. And for that, we're going to focus on the 2D case and deterministic mechanisms. Okay, so we're shifting to a different objective. Now we're going to look at the objective where instead of minimizing the maximum distance to any point, we're going to want to minimize the average costs to the points. Now, without predictions and for deterministic mechanism, the Cornelian-wise median mechanism is again the mechanism that achieves the best known approximation. In 2 dimensions, it achieves the square root of 2 robustness. Okay. So now at this point, you might ask, why are we focusing first on 2 dimensions and we're not looking at 1 dimension? Well, on the line, the median mechanism is optimal. So there's no point adding predictions. We already get an optimal solution. So let's focus on the 2D case where the Cornelian-wise median mechanism achieves the square root of 2 robustness. Here's going to be our mechanism with predictions. It's going to be different than the one we saw before. Here we're going to have to pick a confidence parameter C. This is picked by the designer. Next, we're going to have 2 sets of points. The first set of point P is going to be the n preferred points reported by the agents. And the second set of points P prime, these are just going to be C times n copies of the prediction point O hat. Okay. And next, what we're going to do is that we're going to simply run the Cornelian-wise median mechanism on the union of these 2 sets. So in other words, what this is doing is that the larger our confidence C, the more copies of the predictions we're going to have, which is going to drag our facility towards the prediction. And the smaller the C, the least amount of weight we will have on the prediction points. Now, this mechanism achieves the following strange looking trade-off of square root of 2c squared plus 2 over 1 plus c and square root of 2c squared plus 2 over 1 minus c. The difference here in consistency and robustness is this 1 plus c, 1 minus c over the denominator. But now what is really nice about this result, and maybe a bit surprising, is that this is actually the optimal trade-off that you can achieve for the Euclidean cost. So there's no deterministic anonymous strategy-proof mechanism that can achieve a better trade-off. Okay. So this completely characterizes the optimal Pareto frontier for consistency robustness, which is illustrated here. So this is the most technical result from this talk. How we achieve these bounds for our mechanism is that we're going to be able to completely characterize what is the worst case instance. And then we're going to take any arbitrary instance and we're going to do multiple slow modifications to this instance to slowly change it into this worst case instance, where we have to argue that every change in the instance only makes the cost of the mechanism worse on the new instance. And there's going to be a lot of geometric arguments to argue this. Okay, so now in the remaining time, I still have 5 minutes. I want to mention some other work on facility location with predictions and some open problems. Okay, so there's been several other papers that has looked at strategic facility location with predictions. I won't go over all of them. I will just mention maybe a few of them. There's this interesting paper by Barak Gupta and Targam Cohen that considers a new model for algorithmic prediction that's called MAC advice. And so I think this is an interesting model that could even be interesting for algorithmic predictions beyond strategic facility location, where they assume that the predictions are mostly and approximately correct. So here what that means is that you get predictions about the alien preferred points. And these predictions, there can be a small number of points that are for which the predictions is arbitrarily wrong. Okay, so they have this notion of most and approximately correct that I think is pretty interesting for algorithmic predictions. And they can still obtain very strong guarantees if the number of points that are predicted poorly is small enough. There's this very recent stock paper that looked at the coordinate median mechanism without predictions. So in this paper, for the utilitarian objective, we didn't understand completely the performance of the coordinate median mechanism. All that we knew for higher dimension about this coordinate median mechanism for the utilitarian objective and higher dimension is that it achieves an approximation that's upper bounded by square root of d, and we didn't have a super constant lower bound. So the approximation achieved by this mechanism could be anywhere between constant and square root of d. Since we didn't know what is the approximation ratio that is achieved by this mechanism without prediction in higher dimension, this is the reason why we didn't look at the utilitarian cost in higher dimension, because we don't understand it without prediction. And what this nice paper does is that they can show that coordinate median mechanism actually achieve a small constant in terms of approximation for the utilitarian objective. In terms of open problems, so there's like these gaps for randomized mechanisms that I mentioned in the talk that I think would be nice to close. And now two other directions where there's some interesting open problems is beyond one facility and beyond 2 dimension. I will briefly mention the beyond one facility. So if you focus on the utilitarian cost, and now you're allowed to place 2 facilities instead of just a single facility, we know that the optimal approximation is n-2, okay? And this is tight. There's this paper that achieved n/2 + 1 consistency and 2n-1 robustness for this problem. And so I think here a very interesting natural question is whether it's possible to achieve constant consistency and linear robustness. Okay, so that would be something nice to explore. Right before concluding, again, I just want to mention that this talk, we focused on strategic facility location to exemplify how the framework of algorithm with predictions could be used in mechanism design, but it has also been used for many other mechanism design problems, such as scheduling, auctions, and some other problems. So to conclude, mechanism design can really benefit from the framework of algorithm with predictions. For strategic facility location in this talk, I've showed you multiple different regimes where we were able to completely characterize the optimal trade-off between consistency and robustness. But there still remain many open problems with strategic facility location, and there are also many mechanism design problems that haven't yet been studied with predictions that I think would be interesting to study with predictions. So thank you.
I think we have time for a couple questions.
Thank you. Very interesting talk. I was wondering for the first part, I mean, for the main result, you defined the prediction error, but you didn't show the error dependent of the performance guarantee. Was that part of the paper?
So here we have this dependence here in the prediction error.
Oh, okay. I missed this part.
Yeah. So here's the dependence on the error.
So this is tied for
A good question. We don't know if it's tight. There's the guide. We don't know if this dependency on the error is tight. We don't know that. I would conjecture that it is, but I don't know. Yeah.
Okay. Another quick question is any comment on the online settings of this problem? Suppose agents around sequential.
Yeah. Good. So let me say two things about this. The first one is that online facility location has been studied with predictions. So if you look at the online version of this problem where you remove the strategic parts, this has been studied with predictions. There's a paper on that. Now, you could also try to say what about if you combine both online in mechanism design together and augmented with prediction. My PhD student showing here will present a poster on that. It's not for facility location, but it combines online mechanism design and shows how you can combine both of these with predictions. So I encourage you to go see her poster if you want to learn more about it.
Thank you.
Yeah.
Great. Any more questions? If not, I have one.
Yeah.
Which is that sort of putting on my measurable task systems hat on. So a lot of the results you show, I believe are in the Euclidean metric setting. So I don't know if this like makes a ton of sense, like if it's worth studying, but sort of the natural thing that I was thinking about throughout your talk was how much do the lower bounds, upper bounds depend on the Euclidean metric, and do you think that the bounds would be the same, better, worse in a different metric like L1?
Yeah, I think that's a very natural question. I think the main reason why we didn't explore this is even without prediction, this hasn't really been studied, and I think it's natural to look at it. I haven't thought a ton about it, so I wouldn't go so far as like trying to like conjecture what I think would be the bounds there. But one thing I will mention is that oops, I was in, sorry, 2 seconds. So even though I said that like it hadn't really been studied in related work prior to our work, this very recent stock paper that I mentioned, they have results for the Cornelius median mechanism that holds for any LP metric. So and they can get a constant for any LP for any P.
Yeah. Cool. Thank you. Yeah. All right, let's thank the speaker one more time.